Welcome to Radiation Safety Training. This course will walk through the fundamentals of radiation, including how it behaves, where it's found, and what you need to do to work safely in environments where exposure is possible. By the end of this training, you should understand the key terminology associated with radiation and how it's used across different industries. You'll also learn where radiation exists naturally, including what's known as naturally occurring radioactive material, or NORM, as well as how man-made radiation is introduced into the environment. In addition, we'll cover how radiation is regulated and what risks it presents, along with practical ways to prevent exposure in the workplace. Radiation is a form of energy that moves through space and cannot be seen, tasted, or smelled. It can come from natural sources or be produced through human activity. There are two main types: particle radiation, which includes small particles like alpha and beta, and electromagnetic radiation, which includes energy waves like gamma rays and X-rays. These types behave differently when they interact with the body. Alpha radiation cannot penetrate the skin but becomes dangerous if it enters the body. Beta radiation can travel a bit further and may pose a risk through contact or internal exposure. Gamma radiation is much more penetrating and can pass through the body, making it the most significant concern for external exposure. A key concept in radiation safety is ionization, which occurs when radiation has enough energy to remove electrons from atoms, creating charged particles. Lower energy forms of radiation, like radio waves or microwaves, do not cause this effect and are considered non-ionizing. Higher energy radiation, such as ultraviolet light, X-rays, and gamma radiation, is ionizing and can damage tissue. These types of radiation are commonly found in workplaces like healthcare, research, nuclear operations, and manufacturing, which is why proper recognition and control of these hazards is critical. High-energy radiation is used across a wide range of fields. In medicine, it supports diagnostic imaging and cancer treatment. In industrial settings, it helps measure material properties like thickness and density, sterilize equipment, and reduce static electricity. It's also used in space exploration, long-life power sources, and power generation, including nuclear power plants. Even food safety relies on radiation, with many countries approving irradiation to eliminate bacteria and extend shelf life. Radiation also plays a key role in more specialized applications. In chemical processing industries, it's used to evaluate material density, thickness, and structural integrity. It's also used in military applications, including weapon systems and submarines. In safety systems, radiation is used in devices like self-illuminated exit signs. These examples highlight how common radiation use is across different industries. Ionizing radiation is used in a variety of everyday tools and processes, including gauges, smoke detectors, and systems that reduce static electricity in manufacturing. It's also used in scientific applications like radioactive tracing. While these uses are valuable, history shows that improper use can be harmful. For example, X-ray machines were once used in retail settings to measure shoe fit, but were discontinued once the health risks became better understood. Radiation is a natural part of the environment, and all living things are continuously exposed to it. Scientists have studied radiation for over a century, and we now understand that exposure comes from two main categories: natural background radiation and man-made radiation. Natural background radiation comes from several key sources, including cosmic radiation, solar radiation, terrestrial sources in the Earth, and radon gas. The level of exposure can vary depending on factors like location, altitude, and environmental conditions. For example, people at higher altitudes, like airline crews, are exposed to higher levels of cosmic radiation due to reduced atmospheric shielding. In addition to cosmic sources, radiation is also present in the Earth and environment. The Sun produces both energy waves and particles, with intensity varying during solar events. At the same time, naturally occurring radioactive materials are found in soil, water, and rock. These materials, such as uranium and its decay products, can be ingested or inhaled and contribute to overall exposure levels, especially in areas with higher natural concentrations. Radiation exposure doesn't only come from the environment. Every person has small amounts of radioactive material inside their body from birth. including isotopes like potassium-40 and carbon-14. Some of this exposure comes from food and water, while other sources, like radon, are inhaled. While internal exposure levels are relatively consistent for some isotopes, others, like radon, can vary significantly depending on where a person lives. In fact, radon alone accounts for a large portion of overall radiation exposure in the United States. Radon is a naturally occurring radioactive gas that forms from the breakdown of uranium in soil and rock. As it is released, it produces additional radioactive particles known as radon daughters. These particles exist in small amounts in soil, water, and air, but levels can increase significantly in areas with higher uranium content. Radon can enter buildings through foundations and construction materials, especially in poorly ventilated spaces where it can accumulate over time. When radon and its decay products are inhaled, they settle in the lungs and emit radiation. This exposure increases the risk of lung cancer, particularly with long-term exposure at elevated levels. Radon is one of the most significant contributors to overall radiation exposure and varies widely based on geographic location. According to health data, it is the second leading cause of lung cancer in the United States, after smoking. In addition to natural sources, radiation is also created through human activity. Man-made radiation is produced by accelerating particles and directing them at a target, which generates high-energy radiation such as X-rays. Although these sources are artificially created, their effects on the human body are essentially the same as natural radiation. This makes proper control and safe handling essential in any setting where these sources are used. Government agencies regulate radiation exposure to protect both workers and the general public. In the United States, the average annual exposure is approximately 360 millirems, with most coming from natural sources. The remaining exposure comes from man-made sources, especially medical procedures. Everyday products and materials, such as televisions, building materials, and smoke detectors, can also contribute small amounts of exposure. Beyond common sources, additional exposure can occur through the nuclear fuel cycle, which includes mining, processing, and disposal of radioactive materials. Exposure can also come from the transportation of radioactive materials and historical events such as nuclear testing or accidents. In extreme scenarios, such as nuclear warfare, radiation exposure could be a major cause of harm due to widespread fallout. Workers who are exposed to radiation as part of their job are monitored using devices such as dosimeters, which track accumulated exposure over time. Certain occupations, including airline crews, healthcare professionals, and workers in nuclear facilities, experience higher exposure levels than the general population. Regulatory agencies set strict limits to control these exposures and protect worker health. Radiation can be measured in several ways, including the strength of the source, the energy of the radiation, and the level present in the environment. However, the most important measurement for worker safety is the radiation dose, the amount of energy absorbed by the body. This value helps determine potential health risks and is the basis for exposure limits. Radiation is measured using instruments such as survey meters and dosimeters. Survey meters detect radiation levels in an area, while dosimeters measure personal exposure over time. Historically, units like the Roentgen were used to measure radiation, but modern systems provide more precise and relevant measurements for safety monitoring. Radiation use is regulated by multiple agencies, including OSHA, the Department of Energy, the Nuclear Regulatory Commission, and the EPA. These organizations establish standards that define exposure limits, required safety procedures, protective equipment, and monitoring requirements to ensure safe working conditions. The Nuclear Regulatory Commission is responsible for regulating radioactive materials, including uranium, plutonium, and byproduct materials. It enforces safety standards under federal regulations, requiring organizations to monitor exposure, label materials, post warning signs, and report any loss or theft of radioactive material. Radiation effects fall into two main categories: somatic effects and genetic effects. Somatic effects impact the individual who is exposed, while genetic effects may affect future generations. Some effects appear immediately, while others develop over time, depending on the level and duration of exposure. One of the most significant long-term effects of radiation exposure is cancer, which may develop years after exposure. The type of cancer often depends on how exposure occurs. For example, inhaled radioactive material primarily affects the lungs. While genetic effects have been observed in animal studies, they have not been conclusively demonstrated in humans at typical exposure levels. Radiation exposure has been linked to several types of cancer, including leukemia and cancers of the lung, breast, and digestive system. However, it is important to understand that these cancers can also occur naturally or from other causes. Lifestyle factors such as smoking and diet also play a significant role in overall cancer risk. Although studies of workers exposed to low levels of radiation have not shown clear harmful effects, safety practices assume that any exposure carries some level of risk. Higher doses increase the likelihood and severity of health effects. Historical events, such as atomic bomb exposures and nuclear accidents, have demonstrated the impact of high radiation levels. Radiation risk refers to the probability of harm resulting from exposure. This probability increases as exposure increases. Even though individuals are already at risk of developing cancer naturally, additional radiation exposure slightly increases that likelihood over time. Risk can also be understood in terms of population impact. For example, small increases in exposure across a large group can lead to a measurable increase in cancer cases. While individual risk changes may be small, the overall impact becomes more noticeable at the population level. It is important to understand that probability does not guarantee outcomes. A person with a higher statistical risk may never develop cancer, while someone with lower risk may. Radiation exposure slightly increases risk, but it is only one of many contributing factors. Two of the most effective ways to reduce radiation exposure are minimizing time near a source and increasing distance from it. The less time spent near radiation and the farther away you are, the lower the dose you receive. Shielding materials such as lead, concrete, and water can significantly reduce exposure, especially from penetrating radiation like gamma rays. Containment strategies keep radioactive materials isolated and prevent them from spreading into the environment. Managing radioactive waste involves isolating contaminated materials and keeping them separate from clean materials. Proper storage and labeling help reduce exposure and ensure safe handling over time. When contamination occurs, equipment must be carefully cleaned and verified using monitoring tools. This process involves identifying contaminated areas, cleaning them thoroughly, and confirming that radiation levels are safe before removing items from controlled areas. Personnel decontamination involves inspecting the body for contamination, cleaning affected areas, and repeating the process until radiation levels are cleared. Proper procedures and protective equipment are essential during this process. Radioactive waste must be stored in controlled areas, separated from other materials, and clearly marked. Maintaining accurate records ensures compliance and helps track exposure over time. Workers handling radioactive materials must use appropriate personal protective equipment, including respirators, gloves, protective clothing, and eye protection. These controls reduce the risk of exposure during routine operations. Activities that generate dust, such as grinding or welding, can increase exposure risk. Using ventilation, wet methods, and proper containment helps prevent airborne contamination and protects workers. If radon exposure is a concern, improving ventilation is one of the most effective controls. Opening windows, sealing cracks, and using protective coatings can help reduce radon levels indoors. Workers should remain aware of their surroundings, follow posted warnings, and ensure they are properly trained before working near radiation sources. Monitoring exposure and following established procedures are essential for safety. Workers should never attempt to modify radiation equipment or bypass safety systems. Proper use of monitoring devices and adherence to safety protocols are critical for preventing incidents. Radiation is a natural part of the environment, and complete avoidance is not possible. However, by understanding how it works and following key safety practices, such as maintaining distance, using protective equipment, and practicing good hygiene, you can significantly reduce exposure and protect your health.